Okay. Thanks for the nice introduction of the organizer. I feel very fortunate to present my talk before the Christmas, and I hope everybody we can have a good holiday and enjoy the new year. And I'm very happy to be in Warsaw University. I think it's my first time to be here officially, and of course I visited here just for tourism. So today I will introduce about my recent work about non-Hermitian Fermi-Dirac distribution in persistent current transport. And to start with, I will first thank my collaborator, Zhide Lu from Tsinghua University, and Professor Jose Lado from Aalto University, and my postdoc supervisor, Mia Chachev. He is a team leader in the quantum manipulation group of MagTop. And here is the artistic visualization of the non-Hermitian Fermi-Dirac distribution we found, and in my talk I will show how this distribution emerged physically. We did not conjecture anything to derive such distribution. We have the physical reason to show why we will have this new distribution for non-Hermitian system. All right. Today, as the organizer said, it's the joint seminar of quantum science and technology. So I will try to make some connection between the quantum transport and the quantum information. So luckily, in my own work, we study such connection is through the Ising, SY Ising spin links. I think for quantum information people, maybe you are more familiar with the quantum spin chain, because in quantum spin chain, you can play with the entanglement, such as concurrence, and see how the spin texture evolved. But of course, I focus on another perspective. I focus on the persistent current transport. And first, I will give an introduction about the basic concept about superfluidity, persistent current, and the spin supercurrent. And therein, I will show these two models, the Josephson junction and the spin link. They are made by the Jordan-Wiener transformation. And later, I will go to our main topic of these non-Hermitian systems. And here I want to have a remark that our non-Hermitian system is derived from the Green's function and is totally, entirely for the fermionic Hamiltonian, although they can connect it by the mathematical transformation. But I just want to clarify, I mean, in this part, I did not involve any spin chain. And later I will make a summary. Okay, I think one of our most familiar model for superfluidity would be the helium-4. It captures the dissipationless flow of matter. And because we, as a physicist, we aim to engineer some material, some peculiar phase that matter can flow without dissipation, no matter the information and the energy. And this is the dissipationless flow of matter. And in the last century, I think people found a superconductor can host the supercurrent, I mean, forever, if the temperature and the magnetic field is not so high. And later on, people also found if you connect the superconductor and the normal metal superconductor with a phase bias, not only the superconductor can have a supercurrent, but in the middle, the normal metal can still host supercurrent, and this is called the Jobson effect. And in the last 90s, it's also surprising that people also found a normal ring without any superconductivity can still host a persistent current. But this kind of current, I mean, at first glance, it may feel intuitive because it does not involve any superconductivity. But you are at the price of, because the ring should be very small, because you need to keep the quantum coherence. Because this kind of current is guaranteed by the phase coherence. I will show you later. And that's the dissipationness of the charge. And in our previous work, we made a connection between the superconducting Josephson junction to the Ising, SY Ising spin link. And we show that could host spin supercurrent in the middle part if we have a twisting angle in the right part. And the angle is the isotropic angle. I will show it later. And before we move on, maybe here, because it's more quantum information oriented, so probably people are not familiar with the SNS junction and the normal ring. So here, I will have a brief introduction. So usually we will model this kind of SNS junction by a time binding model. Here, T is the hopping parameter, and delta is the superconducting gap. And as I wrote here, the delta depends on J, which means here, the delta is non-zero. This is non-zero. But for normal metal, it's 0, because the normal metal doesn't have a superconducting gap. And should be careful, I mean, in order to have a persistent current in the normal metal, you need to have a phase bias, as shown in this experimental picture. You have a phase bias in this superconductor, and then you have another phase bias phi 2. And what it matters is that differences. If there is some differences in these two superconductors, that can be a supercurrent floating in the middle part. So that's the so-called Justin effect.
So different modes, I mean different J's correspond to different momenta, or?
Different J?
Yeah, I mean in the sum for Hamiltonian.
The sum for Hamiltonian, there is no, yeah, the J is the site.
Yes.
The time binding, the position of the fermion.
How many J's?
Well, it's a time binding. It depends on you. If you want to model as large, I mean, more realistic, you can choose 100, right? But if you want to play with toy models, say in our non-Hermitian system, because we want to show exceptional points later, so we choose 4 plus 4 plus 4. Say for example, this is 4 side, this is 4 side, this is 4 side. But it doesn't matter because we just want to highlight the effects of EP. So that's why we choose this mode. Yeah, I mean, that's a very good question because usually.
Think about these J's.
Yeah.
It's representing some localization of excitations, yes, or what?
The J. Localization, excitation, I think it's just the Fermionic annihilation and creation operators.
Yeah, but I create fermion with given J.
Yes,
yeah. I have electron at given site.
Exactly. Yes.
So that's like localized mode.
Yeah, localized mode, one year stay. Yes, exactly. Okay. Yes, and that's the superconducting Hamiltonian, the time binding second quantized. And here is the ring. The ring is more simpler, because it doesn't have the superconducting gap. And this is indeed a very simple model. So here I wrote in a very generic way. General way is like it's J dependent. And as long as you set a periodic homogeneous ring, which means all the Tj equal to the same T, then you can solve here. I have an arrow, long arrow here. It's an exercise. I mean, if you can solve it, it's very easy. So you can see, you can analytically solve out is eigenvalue. So as you can see, the K, the usual K. I mean, this K, the quasi-momentum is the usual textbook quasi-momentum. But here, because I have a magnetic flux, so this quasi-momentum will stay the same, but in the eigenvalues, that could be another phase induced by the magnetic flux. And also, its wave function will be encode the magnetic flux. So it's more like the AB effect, I mean, around the Born effect. Okay, and how to compute the current is like you just simply take the derivative of the eigenvalue here with respect to phi. And then you sum all the energies below the Fermi level. So that's the usual technique in the solid-state physics, because solid-state physics, we care about the low energy excitation. So we assume zero temperature. In the zero temperature case, all the contribution of the current should be contributed by so this is the spectrum, by the energy below the Fermi level. So here I said the Fermi level equal to 0. So you should take the contribution from all the states from below the Fermi level. So this is the spectrum, this is the current, if I compute by this formula. And there could be some discontinuity. I mean, it's very normal because here you have level crossing at the Fermi level. So this discontinuity is not very surprising. It's very usual in such very perfect case, because now we assume all the T are the same. I mean, if your T, I mean, dependent on J, you have some disorder, then that will open a gap. I mean, this will curve. I mean, that will be, it cannot be continuously connect to the level below. Okay, so, but it's a bit surprising. You see, in our usual life, we don't feel any current in the normal metal. So why I say this ring has current? So actually, I mean, as I note here, I mean, the ring is very small. It's 1 micrometer. And the current it generated is just 1 nano ampere.
So
but
this is the current in the ground state, or what?
Yeah, we assume zero temperature. Zero temperature.
So it's a ground state.
Yeah, the ground state, the many-body ground state, exactly, yes. The many-body ground state, if you interpret in the Fermionic language, is generated by all the single particle energy below the Fermi level. Yeah, and this is very perfect because, as I said, this current is very small, but it's indeed experimentally observed. But even it's observed, I mean, in order to observe such very small current, you need to make the ring very clean. I mean, you should avoid the phonon interaction. The phonon interaction is like some electron second order interaction, then it will give you some emergent phonon interaction. So that's the jargon of the solid state physics. And this effect can randomize the energy and the phase of the electron and cause the decoherence. Because if you can just imagine if your phase are completely random, so the current, if you sum together, you will just be zero.
So can you say what exactly physically is this ring? I mean, is in this picture?
Yeah, this picture. Yeah, it's just a copper.
Okay.
Yeah, it's just a copper, but just make it.
But cooled to something reasonable, no? I mean,
Yeah, sure. Should be the temperature should be very low. Yeah, zero temperature, absolute zero. Yes.
so it's very cold metal, but not superconducting.
Yeah, it's non-superconducting. Yes. Okay, so now, yeah, because yesterday, 2 days ago, I gave a talk in IFPAN, and Amelia suggested me to give an introduction for the Jordan-Wiener transformation and as a tutorial for students. Yeah, I think it's very easy. So because now we are talking about the Fermionic system. So in 1D, there is a trick for you to map a 1D fermion to 1D spin chain, spin half. So let me introduce. This is the spin chain. You can imagine each ball is a spin half. And each spin, they have some anisotropy. So here is easing. Easing, usually the easing is like you have sigma x, but here I generalize it to be, because here I need to rotate to some angle, right? So you can imagine this M is, you see there's this is the rotating angle. And for the usual case, if you align this M to the x-axis, this will be xx, this is yy, and T is the exchange coupling between different spin. Gamma is the anisotropy. So usually, how people solve this spin chain, because it's Pauli operator, so people just usually take a tensor product of all the Pauli operators. And suppose now if your whole spin chain, the number is n, so your Hilbert space is 2 to the power of big N dimensional Hilbert space. So if, of course, you can diagonalize, you can express this matrix into, you can express this Hamiltonian into a very big matrix, 2n by 2n. And you can solve it, but technically speaking, I mean, now the computer, maybe you can just solve 20 spins, right? So it's very hard because the matrix is super big. So what people found in the last century is like they found we can do a mathematical transformation to transform this spin chain to a Fermionic model. So how they do that? They think, okay, because it's a spin half, so I have spin up state and spin down state. So I imagine each spin up corresponding to one fermion occupied. Here, the subscript refers to the space. So here I have the spin up in the spin space, the occupied fermion in the fermionic space, and spin down corresponding to empty. I mean, just you ask if there is fermion occupied or not. So that's the state corresponding, because intuitively we want to make such mapping. But we indeed need to have a mapping between operators. So a naive way, you can achieve such mapping. You may think, okay, I just map the spin letter up to the creation operator of the fermion, and the spin letter down to annihilation of the fermion, and the sigma z corresponding to kind of the number operator. Say, for example, if this is 1, because the fermion can only be 1 or 0. If this is 1, then sigma z is 1. If this is 0, sigma z is -1. So that's a very naive assumption, right? But unfortunately, it's wrong. Because if you make such transformation, you'll find if you do some algebra, you'll find it doesn't follow the usual anti-commutation rule of the fermion. So that's why you need to add this string. Okay, because just now we said plus corresponding to creation. So here you need to map the plus to this one and with this very long string. So let me explain more further. So here I have the J, that's the side of the spin, and that's the side of the fermion. But when you do such kind of mapping, you need to add a very long string. You should start arrow from 1. Say, for example, if I want to map this spin to a fermion, then I need to add 1, 2, 3, 4, 5. I need to make a product of all the fermion in front of me. But of course, you can prove. I mean, it doesn't depend on where you start. If you want to map, you can count it from here, 1, 2, 3, 4. It doesn't matter where you count from. But I mean, if you do some exercise, you can verify this kind of mathematical mapping can fulfill the Fermiani anti-commutation rule. Okay, so you do such kind of mapping, and then you do some algebra. You compute the easing interaction. Yes, this is in the x-axis. This is in the y-axis, and you do some algebra, and you end up with this Fermiani operator, and then you substitute. Say, for example, you just replace this part. Of course, it contains some angle, right? I'm just saying if you don't, if your phi, your twisting angle is 0, then this is just be x, this just be y, and then you just map this x to fermion in this way, and then you simplify your Fermiani operator. You will end up a very simple projected Fermiani Hamiltonian. And I want to highlight this mapping is mathematically exact. You can do a small exercise.
Sorry, but the problem was on the edges. You mentioned why you cannot do this simple tree.
On the edges?
Yeah, I mean, you gave the argument why you cannot do this simple mapping. So what was the argument again?
Oh, sorry, maybe I confused. I'm not saying, I just say it doesn't matter where you come from. So I was talking about this product. You see, you should have a product smaller than J. But it just depends on how you label the spins. So if you label 1, 2, 3, 4, 5, then if you want to map this spin, you can map to a fermion here, but you need to have a product between 1, 2, 3, 4. You need to add a product in front of the spin so as to maintain the Fermiani anti-commutation rule. But it doesn't matter if you count it from here, 1, 2, 3, 4, 5, 6, 7, 8. It doesn't matter. It doesn't matter where you come from.
Yeah, but I cannot make periodic boundary conditions. I cannot make it in a ring.
Oh, you can. But you need to have some trick. You need to consider the anti-boundary condition. You need to discuss two cases. Yeah. So I mean, that's why in the last century, I mean, there's a very key insight. The last century, people indeed saw the periodic boundary condition, but you need to discuss two cases. Yeah. So here, for simplicity, I only care about open boundary condition. So for the open boundary condition, you have a quadratic Hamiltonian, and the trick for the solid state physics is like we assemble. Because it's quadratic, I think in linear algebra courses, you also learn, I mean, a quadratic polynomial, you can take out the variables, right? I mean, the left-hand side and right-hand side, and what you left in the middle part is just a matrix. There is no operator anymore, because people may scare about the second quantized operator, but if you carefully assemble to be a matrix, everything will be so simple. So here, the C contains all of the Fermiani and creation operators here. So that's a tree widely used in the superconducting community. So this H in the superconducting community, people call it first quantized, single particle, or kernel, or BDG, whatever. But they are indeed the same thing. It's a matrix. Okay. So one remarkable thing is like, you see previous 2 to the power of n is reduced to 2n dimensional reduced Hilbert space for the single particle Hamiltonian. So what we left is this single particle Hamiltonian. Once we solve the eigenvalues of this, we can assemble back to the many-body ground state. Okay, so I want to, because I want to write it, see more carefully, it's like I have the same quantized and I just rearrange the terms and write it. Those are just matrix elements. I mean, you just carefully do the algebra and you will end up with a matrix and leave all the operators on the left-hand side, right-hand side, and then what you need to do, now you just diagonalize this matrix using your linear algebra diagonalization. And later, you diagonalize with some diagonal matrix, and this is called the D is in the superconducting community is called the Bogoliubov, because after the Bogoliubov transformation. So D is a new kind of Fermionic operator which can diagonalize your Hamiltonian. So now your eigenvalues has n different values, so you can use different values of n to, as I said, to assemble back to the many-body ground state. So be careful, this is the single particle eigenvalues, but in the original picture, you are dealing with a many-body ground state. So what I'm saying is here, I mean, people, in the notation, we just use we diagonalize the H, the matrix, to be a sum of all the eigenvalue and eigenfunctions. So this is not a fictitious function. It has real physical meaning. It's called the single particle wave function. Okay, and I think in the last century, the condensed matter physics focus on the topological insulator and superconductor. Usually people don't look at the many-body second quantized Hamiltonian. Usually it's sufficient to look at this matrix, then to do the symmetry classification, whatever. So that I think in the last decade, people are focused on analyzing this matrix to analyze the topological invariant. So, yeah, a bit messy. I think I spent too much time here. I need to speed up. I want to say for normal metal is like you don't have superconducting pairing. This part is a 0. This part is also 0. So for the normal metal, you can just use those single particle wave function to build up the many-body wave function. That's the many-body wave function. That's the single particle wave function. And for superconductor, the many-body ground state is found to be, that's the BCS theory, just sum all of your annihilation operator, this D, and then if you express D in terms of the fermion, you will end up with the wave function. That's the wave function, okay? That's the wave function, the single particle wave function. So that's why I want to make it clear. Our work is later. I mean, our non-Hermitian work is built on this Green's function, where maybe.
Sorry to interrupt you once again.
Okay.
So when you say quantum speed change becomes exactly solvable,
yes.
You mean the ground state or all energy?
All, yes, everything.
So you don't lose anything.
Everything is exact.
Even though you had 2 to the n.
Yes.
Space,
yes.
Everything is degenerate. I mean, like you have eigenstate.
Yes.
In this new.
All the excited state I can give.
You find all energies.
Yes, all energies.
But you need to throw a lot of compute on it, right?
So it depends on if you are not homogeneous. Say if your Tj depend on J, right? Random number, then actually you need to numerical diagonalization this H, this matrix. Yeah, you need to do numerics. But if your T delta are uniform, then you can get an analytical result. It has been solved in the last 50s. Yes. But of course, there is no free lunch because now we are in a different picture, in a different basis. If you want to transform back to the spin chain, then it's a bit messy because you need to do the non-local transformation again. Yeah. So no free lunch. Okay, so yeah, maybe I'm here. I just want to highlight. I mean, in the condensed matter physics, the single particle wave function is indeed has a very clear physical meaning. It doesn't mean this is a very handmade wave function. It has a real physical meaning. All right, I think I spent too much. Let's give me a summary for this part. So just now, I mean, we map the Ising, SY Ising, and to a superconductor normal superconductor. They are one-to-one mapping. So here, the twisting angle of the right Ising part has mapped to the superconducting phase. And the fermion is spinless. Yeah, I forget to mention, those we don't have any spin degrees of freedom because, as we know, in real life, the fermion has spin degrees freedom. You can have spin down, spin up. But in such a mapping, you don't have spin. So if you talk to the topology, if you talk to the solid state physics, this is called the topological insulator or the P-wave superconductor. Because the S-wave is like the spin up is paired with spin down. But here, because you don't have the spin, so essentially, all your spin are pairing in the same direction. So that's called is P-wave. And P-wave, that in the solid state physics, that can be Host-Majorana. That's another topic. But I think you must heard of the Majorana can be used to do quantum computation. And yes, and it's more robust. It's topological protection. But today I don't want to talk about topology. Today I want to talk about how to compute the current operate, how to compute the persistent current in the middle part. So as we know, the current operator, if you write in the spin space, is just in this form, in Pauli operator. And if you do the Jordan-Wiener transformation, it will become a Fermion operator. And because it's quadratic, we can use the same trick to write in a quadratic form. And again, this J, curly J, is a matrix. And in the solid state physics, we know there's an identity how to compute the current. So as we mentioned about, a professor said, the ring, I mean, we are indeed focused on the ground state because only in zero temperature, we are in the many-body ground state. So how to compute the current is just like you take the derivative of the many-body ground state with respect to phi, and then you get the current. But if you map to the fermionic picture, because those fermions, they are non-interacting, so you can decompose the many-body ground state to be a sum of all the single particle eigenstates below the Fermi level. The Fermi level is 0. So that's one identity. Another identity, you can just sandwich your operator with a single particle wave function. And later, you can have trivial Z2, Z4. I mean, it's a jargon again, but trivial is very simple. It just means your current follows the same periodicity with the Hamiltonian. And Z2 means, okay, suddenly you have some additional degeneracy. Then you can double your periodicity to be 2 pi, 4 pi. So here is again 2 pi double to 4 pi, and maybe sometimes become 8 pi. So that's called the Z4 Josephson Fab, etc. Okay, then I think I should speed up. And for the current, I mean, in our previous paper, we know we found the periodicity of the current depends on the parity of the middle part. We found if the parity in the middle part is even, then the current will have 2 pi come back to its original state. And if the middle part is odd, then you need to have 4 pi periodicity to come back to its initial state. And later we discuss how to detect such current because this is half spin chain. It's very small spin. It's not so large spin. So of course, in usual case, in condensed matter physics, you can use inverse Hall effect to detect the spin current. But that kind of approach will destroy the spin current inside. So here, we want to invasively detect the spin current. So that's why we first couple the spin chain to a cavity. But be careful, this cavity is called a circuit QED. I mean, it's not a visible line. It's M hertz and million hertz. That kind of level. So it's microwave. Yeah, technically speaking, it's microwave. So I couple to a cavity, and then I have some input field and output field. I measure there are differences, and then I can observe some different signature of the even or odd pattern. So that's the detection scheme. So that's the overall, of this paper related to the spin chain. But later, we want to discuss the persistent current transport if the system interacts strongly with the external reservoir. So later we found, we can use the non-Hermitian quantum Hamiltonian to capture the transport. So here we call it quantum Hamiltonian. Of course, we follow some literature, but of course we have some reason why we call it quantum. Because it's second quantized. It's attached to, as I said, it's attached to the fermion operator. It knows the statistics. It knows it's boson or fermion. So that's why we call it quantum. And again, it's Hamiltonian. Maybe Hamiltonian is not so appropriate. As I know, if you later we look at the Lagrange equation, maybe it's more appropriate to call it a dynamical generator. I will show later, but it's just a terminology problem. Okay. Then, how to study the Limbla? How to study the effect of the environment on the Hamiltonian, on the system? Usually, there are two approaches. So I think for quantum information people, maybe you are more familiar with the Limbla because Limbla is more easier. And you just have a density matrix, reduced density matrix. The total system is a rho t, but you can focus on this small rho and then model the effect of environment by the Limbla dissipator. And that's one approach. Yeah. But unfortunately, out here, I want to highlight our work does not rely on Limbla. And I want to make a clear collaboration. We don't our non-Hermitian, we do not touch the PT symmetry Hamiltonian. So what's called PT symmetry? Because some people, they want to reinvent the quantum mechanics in a non-Hermitian way. It's more about mathematical physics. But I want to say here, we did not invent anything. We derive from the Green's function. And non-Hermitian effect is an emergent, it's a physical effect. Okay, so what do I say? Yeah, maybe it's, again, I need to use some solid state technique from the quantum transport. So in the quantum transport language, if the system is isolated from external reservoir, then you can diagonalize the system and each level is just a data function. But if you couple to the reservoir, your level will be broadened by the interaction. So you see here, essentially, initially there should be some level here, but once you couple to a reservoir, your level will be broadened. So that's the language of in terms of quantum transport. And mathematically, it's exact. If you can compute the self-energy from the reservoir, and usually if we want to obtain some analytical result, you need to assume some limit approximation. So usually people call the wideband limit. And if you add this wideband limit self-energy into your original Hamiltonian, this is the Hermitian Hamiltonian. Then you have some non-Hermitian matrix that characterize the dynamics of the system. Okay, so again, this is the microscopic level because here I did not draw what's inside the reservoir. So how we model the reservoir is a localized mode, 1, 2, 3, 4, and they have hopping, infinite hopping. Okay, then we want to study how the system is affected by this reservoir. And okay, I want to have a matrix. It's very easy. This is the matrix and this is the basis, second quantized. And what it modifies, I add the self-energy here because that's the self-energy. You can compute it. And because all the physical effect happens around 0. So that's why we take the wideband limit of sigma omega approximately equal to 0 because all the intrinsic physics happens here. So we can assume this approximation to implement the calculation. All right, so let me summarize the approach. So first we have the self-energy and we made the wideband limit approximation. And then we get a non-Hermitian matrix. Because this is non-Hermitian, if you know some linear algebra, then you will know if your matrix is non-Hermitian, then you will get complex spectra. That's the real, that's the imaginary. And the question naturally arises, so how do we generalize this persistent current formula to the non-Hermitian case? So specifically, we consider a concrete model is called a Josephson junction coupled to Fermiani reservoirs. So here we couple to two reservoirs, and people may be interested, why we couple to those reservoirs? We do not couple them just by funny. Actually, we want to model some effect, such as the quasi-particle poisoning. I mean, because in real experiment, nothing can be perfect. You must interact with the system, so that must be some particle influence your system. Also, I mean, in this paper, I mean, people deliberately, I mean, they couple a resistive normal lead, I mean, to the system. So we have different motivation to model the non-Hermitian system. Okay, so let's see the spectrum. The green line is the spectrum before the system coupled to the reservoir. So as we know, if I diagonalize the matrix, I get the real part and the imaginary part. And we can see this isolated spectra is shifted to the black one. And this curve is more even fascinating because you will have a pink zero mode. You see the state will be pink here. And for the imaginary part, that would be a circle. And here is nothing. I just plot this real part here and the imaginary part here. And you see the eigenvalue will show this very peculiar.
Why do you have symmetry between plus-minus energies?
You mean plus?
You have both positive and negative.
Yeah, that's a very good question. It's the symmetry of the superconductor. It's imposed by the superconductor. Yes.
Okay, but physically, what does it mean?
There's particle in hole in the yes.
Okay.
Yeah, there's particle and there's the hole. But another key point is like you see the negative part is all negative. You cannot have positive negative. Yeah, I mean only the real part is symmetric. The real part is symmetric, but the negative, but the imaginary part is always require negative because that's guaranteed by the Green's function. Okay. And later, you see we have another new terminology. It's called the exceptional point. So the exceptional point mathematically means this non-Hermitian Hamiltonian cannot diagonalize at this point. Or say for example, if this is a 2 by 2 Hamiltonian, so your eigenvector will become the same. So you don't have sufficient eigenvector to support your space. So that's why these 2 points are very special. They are called exceptional points. So I will recall you that the Hermitian formula, if you want to compute the current, you need to take the derivative of the single particle energy with respect to phi. But I think you can immediately notice if I take the derivative at this point, it will diverge. So that's the tricky point. The question is how to generalize this derivative formula to non-Hermitian system. Yes, how to generalize this formula. And actually, in recent years, it's undergo debate. It's not a trivial problem. It's not a trivial problem indeed. Some people, it's just like they say, okay, I look at this conventional Hermitian formula, and I can make some mathematical conjecture. So the first one is what I said. I mean, they just substitute the real eigenvalue to be a complex eigenvalue, and they calculate the derivative. And as expected, if I calculate derivative here, it will diverge. It will go to infinity. But I mean, these people, they believe, I mean, this might be true, but unfortunately, I don't find it physical because I believe the current cannot go to infinity. Here, I want to add a remark. I mean, this paper, in their archive version, they go to infinity, but in the published version, they remove the divergent result because they did not. They know their formula doesn't apply to EP case. But okay, that's the first approach. So the second approach, if you look at this formula, the first two identities, they care about the many-body eigenvalue and the single particle eigenvalue. And the third one is care about the wave function and the current operator. Okay, they are single particle operator and eigenvalue. And these people say, okay, maybe I just substitute the eigenvector to be left, right, right. And then they compute the current. Again, if you compute by the RR, of course, you won't get the diversion. but you will get some discontinuity at the exceptional point. And if you compute by LR, I mean, no surprise, you will get the same result, the same divergent result as the derivative, because we know, in our paper, we show the LR is the same as you take the derivative of the eigenvalue. So all of these are very suspicious. So that's why we want to know what's wrong inside. I mean, definitely this kind of simple generalization cannot capture the real persistent current. So actually, we indeed thought this problem in 2020. But at that time, as I said, I mean, we focus on the spin link. I mean, that's what we discussed before. And at that time, I compute this. I also get divergent, but we don't believe it. So that's why later we look for some textbook. I mean, we go for the Green's function. In the Green's function technique, they compute the current in a different way by that's called the fluctuation dissipation theorem. It's or equivalent, you can say, is the detail balance. And I compute the current by this formula. It's a numerical integration. And I compute, that's the green line, and that's the green line. And as you can see, no anomalies at the exceptional point. So, which makes me very puzzled. I mean, I know what's the correct way to compute the current, but I cannot get a closed form at that time. What I can do is implement a numerical integration. And except for obtain a closed form, the reason why I want to obtain a closed form, because I want to know why, if I do the integration, I won't get divergent effect, because everything is smooth at the exceptional point. But actually, it's a very challenging problem. But luckily, we recently tackled this problem and obtained the reason why we cannot get a closed form and why we can get smooth curve. So the motivation why we carry out this paper is like, we want to know how to compute the many-body observables in a non-Hermitian system. So the persistent current is just a special case. We can compute different many-body observables, like the energy, whatever. And in our opinion, if you derive the non-Hermitian effective matrix or effective dynamical generator, you should put back your Green's function to calculate. And we found maybe we end up with a different distribution, except for the conventional Fermi-Dirac distribution. And only that we can compute the observable. And finally, after we obtain our result, we compare to other approaches, as I discussed. They compare the expectation value by left, right. Okay, so due to the time limit, I think I just summarized.
5 minutes?
Huh?
5 minutes?
I can catch up. Yes. Yeah. Actually, that's already the key result. But later, I just focus on the details. It's like we figure out, I mean, we need to generalize the usual conventional Fermi-Dirac distribution to the complex plane. So this is the imaginary part. And that's the zero temperature. That's the final temperature. And with the log, that's the zero temperature. And that's the digamma function. And we found you can compute any quadratic Hermitian operator in this way. It's another different way to compute the many-body observable. And we use this formalism to specifically derive how to compute the persistent current, and we end up with this analytical formula for the zero temperature. And as you can see, this blue line is computed by this formula. Everything is smooth, nice, no exceptional points here, no divergence. And later, we compare to other mechanism, the dashed line. Okay, we also do some benchmark. So let me recap. So our formalism, we couple to two external reservoirs. But on the other hand, I can numerically diagonalize the whole system. Because the whole system is Hermitian, I can guarantee I can use the usual Hermitian formula to compute the result and compare to the result of the subsystem. You can think in this way. I mean, the whole system, you have a density matrix. Maybe it's a pure state, but you do a partial trace, then you end up with a mixed state. So, but no matter you compute from the mixed state or from the pure state, you will give the same result. That's from the viewpoint of quantum information. And that's what we did. But I'm just an analogy. I compute from the complex eigenspectrum and compare to the exact one. This is the exact total system. So you can see the dashed line match exactly with the exact transition, and that's for the ring, also the same. In other approach, they are very peculiar. Okay, we don't need to talk about that. And that's the result for the finite temperature. And that's, we also add the interaction to see if I can observe any exceptional point. So again, no exceptional point here. Okay, so this part, I mean, we just want to uncover where is the exceptional point, and we compute this dynamical susceptibility and do some lengthy calculation. But finally, we show the exceptional point can be observed in this susceptibility. And the susceptibility encodes the level transition. So those are the level transition. Level transition means the differences between the single particle energy. Because it's a delta function, if your omega meet the differences, you will have a peak. And we conclude, I mean, the signature of exceptional point cannot be observed in the steady state or in the equilibrium state. If you want to find any signature of the exceptional point, you should look at this dynamical quantity. And this is consistent with the limit law. And again, I want to highlight, we don't use limit law, but our Green's function consistent with limit law. Okay. So the susceptibility can be measured. I mean, this is a picture. You can just have a junction. This is a junction. That's the small junction. And usually people just couple to a multimode resonator. And you measure the frequency shift, you get the real part. And you measure the inverse quality factor, you get the imaginary part. And the current, it just you can infer from the adiabatic limit. Okay, so I will have a final checklist. And in the Hermitian system, I mean, we have I think in quantum information, you also compute the trace rho and this rho. But I want to have a key remark. It's like those operators are the first quantize already written in the quadratic basis, okay? But it shares the same form with the usual quantum information. And that's the usual Fermi-Dirac distribution, the finite temperature, and that's the persistent current. And this is our byproduct. I mean, we obtain the self-energy of the non-Hermitian system. But of course, you should use some special function to compute. Okay, I think this might be too technical detail, but I just want to give you a remark. I mean, if I want to compute, because I mean, 2 days ago I presented, I want to avoid the formula, so people get, even the expert confused by my talk because they thought I was based on limit law, but indeed I'm not based on limit law. I'm using on the Kardashev bound equation. And as I said, I mean, I agree. I mean, we should call this as a dynamical generator because we have a noisy term. Yeah, and it's indeed a Lagrange equation. And our formalism is rely on this integral. And if you want to finish this integral, you need to go to residue theorem. And if you are interested in residue theorem, you can go to my blog. I mean, I have not my blog. It's the Wolfram community. I have a notebook explicit how to do the contour and how to do the contour here. It's in the start pick. I mean, the Wolfram community have a start pick for my notebook. Yeah, that's for the technical detail. And I mean, our paper was posted in March, and luckily, I mean, Professor Binaker, I mean, he is an expert in quantum transport. He support our paper and highlight our paper. And we have some follow-up in May. I mean, people also confirm our findings. All right, we have some outlook for the multi-junction has been done by those people already. And as I said, I mean, the latter part is all Fermionic. If you want to look for some observable back to the spin chain, you can do the inverse Jordan-Wiener transformation. And now we are doing, we want to engineer different non-Hermitian matrices for the Jobson diode, where there's another effect. And we want to generalize our formalism to non-equilibrium system. Okay, I think I'm running out of time. Thank you so much.
So thanks a lot for this very nice talk. I think you did your best to to make it accessible for us.
Yeah.
So we have time for questions. Yes, please.
So just to get an idea about the overall framework,
Yeah.
so if you have a fermionic system connected to a fermionic bar, then in principle we can use your formalism to get an effective Hamiltonian and get the formula for current, right?
Yes, our formula is very general. You can apply to any quadratic free fermions.
Yeah, so what about the type of interaction with the system and the bath? So is there any restriction there? Like should it be quadratic or?
Oh, of course, everything should be quadratic.
Everything should be, okay.
Yeah,
So
we cannot.
Hamiltonian, you can deal with this formalism.
Yes, yes.
Okay.
Yeah.
Yeah, there was another question. Yeah.
Yeah. So you define some effective quantities, yeah? Like effective distribution?
Yes, effective.
Yeah, so what is its interpretation in practice? Yeah, because, okay, I know what is the interpretation of normal distribution, yeah?
Mm-hmm.
This is something that I can measure in principle. And what is this interpretation, the interpretation of this complex distribution?
Yeah, you are right.
Quantities.
You have the key observation is like, maybe you can look here. So as I show in the 3D plot, maybe here, I plot the imaginary part of the effective distribution. And indeed, we're reduced to the usual Fermi-Dirac distribution. And if we look at this observable, we just focus on specific observable. You can see it should be the real part normalized by the imaginary part. But also should be careful. I mean, the imaginary part is also very important. The imaginary part should be normalized by the real part. So to answer your question, I think in this non-Hermitian system, because it's new, I mean, I cannot have the same understanding as the Hermitian case. Because the Hermitian case, you don't have the imaginary part. And this term can be deleted. But in non-Hermitian system, you cannot neglect this term. If you neglect, then you will have discontinuity current. So to conclude, I think this is a new concept. I mean, we cannot have the conventional Hermitian understanding for this non-Hermitian.
Okay, but if I want to again make it like as simple as possible, so your approach from Lindblad to this effective approach, where you throw away this post-selection, by post-selection, these events that somehow represent that the system went to some other state, which we throw away, and we just look at this subspace.
Yes.
If it stays in the subspace,
yes.
where we have this effective Hamiltonian. Okay?
Yes.
So in other words, when you find complex eigenvalue, it means that this state decays.
Yes.
I mean, our system has some probability to be out of this.
Sure,
state.
sure.
So what does it mean then that you compute the current? So does it mean that this current decays exponentially, or?
Yeah, I can show you a backup slide because I did a tiny bit I did not show. So here I do the dynamics, not this one. So here I can answer your question. So the green part is before I couple to the reservoir.
Yeah, so it's like idea, yes?
Yeah, and then suddenly I couple the reservoir to the system, and that's the current. The current will start to fluctuate, and finally it will reach a steady state. I mean, the observable. Of course.
So this is your final current.
Yes.
This final steady state.
Yeah, final steady state. Yes, and it can be effectively captured by my formalism.
And this complex value tells you what about this time scale it takes to reach this steady state?
Oh, we cannot control the time scale because in our formalism we already assume the long time limit. We cannot capture the changing regime here.
Okay.
Yes.
But just a comment. But there's no post-selection, no?
Yeah.
I mean, in a sense, there is, no? When you discuss effective.
No. That's the key. We discussed efficient. So no, you really solve full. It's just an effective picture. It's like I throw away Lindblad description, but I find an equivalent representation that is non-Hermitian.
Yes, another one. Yes.
Exactly.
So
your intuition should be abandoned. It's basically to get this quantity, it's like you have Wigner function that you need with generalized probabilities. Here you have Fermi-Dirac that generalizes to complex plane. No? You say like this. It's like a different mathematical tool.
it's a different mathematical tool. Exactly. We do not rely on Lindblad, but we can borrow some understanding from Lindblad. Okay. And actually, the noisy term acts like the jump operator. We did not throw away the jump operator. We did not assume the post-selection. That's what other people did.
Yes.
Yeah. But in the Lindblad, you write in a different way. But this is a noisy term. It's similar to the jump operator.
So you say that the people who throw away just use this first part?
Yes. Yeah.
Okay.
That's the post-selection.
I see.
Yeah.
Okay. So, last question before Christmas. Can be very general. So, okay, maybe I ask very general question. So, what it has to do with superconducting qubits?
Wow.
Would this understanding help to build better quantum computer based on superconducting qubits?
Yeah, the superconducting qubit, I think it's also built on the Jobson junction.
Yeah, exactly.
Yeah, I
And
hope.
then you need these coherence times to be as long as possible and to manipulate these qubits there. So I was wondering if your physical theory can help to understand better what's going on there.
Yeah, I expect maybe. I mean, our formalism can help people to understand the dephasing mechanism
exactly.
of the Jobson junction.
But we're not working on this.
Yeah, we are not working on this. Yes, thank you for the question.
Okay, so yes, that's it. So let's thank.
Thank you so much.